Hello guys, this is Wits Lounge, Learning Made Easy. And in today's video, we are going to be understanding a very important concept, which is the acids and base. Having said this, we would have to go into the next part of the study, which is understanding what a Lewis acid and a Lewis base is. Let's start with the Lewis acid. As I said, these scientists have actually been looking into the concept of acid and base and notice that some of these definitions do not always apply. There are substances that, for instance, exhibit acidic properties but they do not ionize hydrogen. There are substances that they notice too, that's Mr. Lewis noticed, that doesn't necessarily donate or accept hydrogen. However, it still exhibits acidic and basic properties. That's why he was able to come up with his own definition. Now, before I get into giving you the exact definition, I noticed something, that the Lewis acid definition is somehow like the opposite of the Bronsted-Lowry's definition. I would explain that. Let's before we'll come back to this, but let's look at our board a little bit. A Bronsted-Lowry acid, we already said it is any substance that donates, which means a Lewis acid would do the opposite. It would accept. Now, a Bronsted-Lowry acid donates a proton. A proton. The opposite of a proton, if you are looking at the particles inside an atom, the substance that has the opposite charge to a proton is electron. So just have that in mind. But then it's not just an electron, but an electron pair. So notice this. A Bronsted-Lowry acid donates a proton, but a Lewis acid accepts an electron pair. So that's the basic definition of a Lewis acid. So let's look at the screen as we go further. A Lewis acid is an electron pair acceptor. Any substance that has the ability to accept an electron is what we refer to as a Lewis acid. I take it again. A Lewis acid is an electron pair acceptor. Once it has the ability to accept an electron, it is a Lewis acid. Now, what are the things that might actually enable a substance to be considered as a Lewis acid? Once you notice that the substance requires at least one pair of electrons for its outermost shell to be completely filled, suspect that it is a Lewis acid. The other thing about it is, once you notice that a particular substance has an empty outermost shell, it is most likely a Lewis acid. And the classes of substances that coincide with these properties are things like your metallic ions, your hydrogen ions, your boron trifluoride, and your aluminum trichloride. You get, these are substances that have either empty outermost shells or have shells that would require just 2 electrons to fill them. We'll get to understand them when we take up examples, but just have this in mind. A Lewis acid is an electron pair acceptor. When we talked about the Bronsted-Lowry acid, it was based on proton, and we said that a Bronsted-Lowry acid is a proton donor. But in this case, a Lewis acid is an electron pair acceptor. Okay, now I think you can actually guess the definition of a Lewis base based on what we just said. Since a Lewis acid is an electron pair acceptor, the Lewis base would have to be the electron pair donor. And what does this mean? Before you consider a substance to be a Lewis base, it must possess electron pairs. I take it again. We look at the screen again. Lewis acid, electron pair acceptor. Lewis base, electron pair donor. So have that in mind, that whenever you are considering a Lewis acid, it has to accept an electron pair, which means for it to have the ability to accept, it means that it requires a pair of electrons. What are the properties that you would see and you would know that it requires it? Number one is that the outermost shell is empty. It has lost all the electrons in the outermost shell, and the substances that lose their valence electrons are metals. So have that in mind, that metallic ions are going to coincide with Lewis acids. On the other hand, Lewis base are electron pair donors. Any substance that has a lone pair of electron can actually act as a Lewis base, because for you to donate an electron pair, you must have that pair of electron, and that's what I mean by the lone pair. So basically, if for instance I consider something like water molecule, let's consider the shape of water molecule. It's more like angular in a way. So considering the atomic shell of oxygen, which is the central atom, you have 1, 2, 3, 4, 5, 6 basically electrons on the atomic shell. Now hydrogen comes along and then becomes attached at this end. It forms a covalent bond at this end. Another hydrogen comes along and forms a covalent bond at this end. Now what I want you to notice is this: there are two pairs of electrons that are alone, and these pairs of electrons are referred to as lone pairs. So once you have a pair of electrons that is not involved in covalent bonding, that pair is what we refer to as the lone pair. Now this particular pair that is involved in the covalent bond is what we call the shared pair. So have that in mind, that once you are a Lewis base, you must have a lone pair. If you don't have a lone pair, you most likely will not be acting as a Lewis base. Every Lewis base must possess at least one lone pair of electrons.
Another group of substances that can be considered as your Lewis base are your anions of non-metallic elements. So things like your oxygen anion, your fluorine anion can also be considered as your Lewis base.
Okay, having said that, the other thing I would like to say about the Lewis base is that a Lewis base that is attached to a metallic ion is most times referred to as a ligand. So any substance that donates an electron pair in a complex ion when it is attached to a metallic ion is what we refer to as a ligand. So you might hear that often. Ligands are basically Lewis base attached to metallic ions. So once you think about a ligand is basically a Lewis base that is attached to a metallic ion. One of the reasons they are called Lewis base is because they donate their electron pair. So every Lewis base must possess what we refer to as a lone pair of electrons. So coincidentally, or the implication is that water can actually serve as a Lewis base because it has a lone pair. Now I have ammonia represented by NH3, and basically ammonia has a lone pair of electron and hydrogen attached here, here, and here. If it is reacting with hydrogen ion, which one of them is a Lewis acid, which one of them is a Lewis base? I've said this already, that once you have a particular atom in a molecule which possesses a lone pair of electrons, suspect that that guy is a Lewis base, and yes, automatically this is our Lewis base because it has a lone pair of electron. You get? Now in this case, these are Lewis acid. Why is it our Lewis acid? Because it accepts this lone pair of electron, and that is what leads to the formation of ammonium ion. Okay, let's use a different color so that we can differentiate between the hydrogens there. Okay, so imagine, let's use red. This is hydrogen ion. Okay, so this hydrogen ion accepts this particular electron pair for it to be stable to form what we call a coordinate covalent bond. A coordinate covalent bond or a dative bond. The coordinate covalent bond is a form of sharing of electrons in which only one of the combining atoms contributes the shared pair. Basically, we'll get to discuss that in another study, so let's not bother ourselves about that. So you have H, 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 and all together these guys are positively charged because the hydrogen ion submitted its charge. So what do you notice here? The hydrogen ion has an empty shell, and I told you one thing about a Lewis acid is that it either has an empty shell or requires two electrons to be completely filled. Hence, what is this going to be referred to as? The Lewis acid. So Lewis base donates an electron pair, Lewis acid accepts an electron pair, and that is that basically about that.